Okay, welcome to an enrichment for trigonometry. We're going to take a look at the law of sines and the law of cosines. Now, this is just an introduction to these two concepts. There are a lot of little tricks and special things to be careful about when you use law of sines and cosines. This is just giving you the original basics of how to do the math. So, what have we done so far when it comes to trigonometry? We've been working primarily with right triangles. So the rules and the definitions, things like SOHCAHTOA, let us find the missing sides and angles for right triangles. But what if they're not? I mean, think about it. There are a lot of triangles in this world that are not right triangles. There are a lot of triangles in actual life, in construction and architecture and engineering and physics and rocket science. They're not right triangles. If you try to triangulate to find a location, that's not a right triangle most of the time. So doesn't that mean that trig is that limited? It's only good for unit circles and right triangles, so you learn all that stuff and it's really hard and then it only gets used sometimes? Well, of course not. When it comes to mathematics, there is always a way to adapt something we learn on a limited scale into something that can be used across more things. So trig ratios are actually applicable to any triangle. You just need to know a couple of important laws. The first law is called the law of sines. And what the law of sines tells you is if you have a triangle with angles A, B, and C, and the sides opposite to each of those angles, labeled little a, little b, and little c. Turns out that if you do the sine of angle A compared to its side, you will get the exact same scale factor as comparing the sine of angle B to its opposite side and the sine of angle C to its opposite side. That should make sense. A triangle, no matter what it is, has a certain scale factor existing between sides and angles. That scale factor should be the same if you're comparing angles to the side length created by the opening of that angle. So angle C is open a certain number of degrees, creates a straight line distance of little c. If I made angle C smaller, little c would get smaller. If I made angle C bigger, little c would get bigger. And that does create some basic constants. So then how can we use law of sines to find a missing part? So up in the far corner, I left the law of sines for you. But here's an example. Here's a triangle. I have a 60-degree angle, a 20-degree angle, a side length of 10, and I want to find little b. So in order to use law of sines and find a missing side, all we need is the angle opposite of that side, and then we need another angle and its opposite side that both have values. So in this case, we know angle C and little c. We want little b, we know angle b. So what we do is we now set up the ratios. So I know that sine C to little c is going to be equal to sine B to little b. So the sine of the 20 compared to 10 is going to equal the sine of the 60 compared to little b. It's a proportion. I'm just going to solve. I multiplied both sides by b and multiplied both sides by 10 to clear the denominators. Then because sine 20 is just a weird decimal that I don't want to deal with right now, I'm going to divide both sides by sine 20, and I get this thing. Little b is 10 times the sine of 60 divided by the sine of 20. If I now put this into the calculator, making sure I'm in degree mode, and just do the math, I get that little b is approximately 25.3, whatever units. Now, what if I want to know an angle? It's basically the same thing. You set up the ratios, solve for what you don't know, but because we're getting an angle at the very end, we're going to have to do an inverse sine. So here come those inverse functions again. So let's say I want to know angle A. To find angle A, I need little a, which I have, it's 15, and then I need another angle and its side, which I have. I have angle B and little b. So I'm going to set it up. Sine of 55 over 18 equals sine of A over 15. Now I multiply by 15 to get sine A alone. So 15 sine 55 over 18. And then I'm going to do an inverse sine of that whole mess. And I get that angle A is roughly 43 degrees. So why don't you go ahead and try? Here are a couple problems. Try your hand at the law of sines and see if you can figure out. So pause and come back when you're ready. Okay, let's look at some solutions. We'll start with the first triangle. To find little a, I get sine 65 over a equals sine 70 over 26. So if I solve for a, I get that fraction full of lovely math, and I put it into my calculator. A was about 25.1, which really kind of makes sense. If a 70-degree angle produced a side that was 26, something just a little bit smaller would produce a side that's just a little bit smaller. Here's our second triangle. I needed both angles A and B. So I set up to find angle A, which was 51. Now if I wanted angle B, it's just a simple triangle. 51 and 45 make 96. That all has to add up to 180 with angle A, so angle A must be 84 degrees. Now let's take a look at something different. This is called the law of cosines. It's another way that sides and angles in non-right triangles go together. And as you're looking at it, it should look super familiar. So here's the triangle. The law of cosines comes in three forms, depending on which of the three sides you're solving for. What I can tell you is that technically, the law of cosines is one form. You can generalize it quite easily, but for the sake of making sure you know what's going on, we'll call it three forms. You have, if you want the c side, c squared equals a squared plus b squared minus 2 times a times b times the cosine of angle c. You'll notice the other two forms are just the same. The side you want squared is one of the sides you know squared plus the other side you know squared minus 2 times both those sides that you know times the cosine of the angle that goes with the missing side. If it's feeling familiar, like, wait a second, that's the Pythagorean theorem. You are right. That's what makes the law of cosines so incredibly cool. It's the Pythagorean theorem adjusted for non-right triangles. And if you're thinking, well, then what about a right triangle? Because we know the Pythagorean theorem, it's c squared equals a squared plus b squared. That's that top row. Well, change the C angle to 90 degrees, because in a right triangle, C is the hypotenuse, the side opposite the right angle. So if I change C, angle C, to 90, the cosine of 90 is 0. So that whole minus 2ab cosine C goes away, and there's the Pythagorean theorem. Mind-blowing moment. Now, let's use the law of cosines. So I want to find little b. And in order to find little b with law of cosines, I need its opposite angle, and I need the other two sides. Law of cosines does that. It uses three sides and an angle. So here we go. I'm just going to grab the b version, and I'm going to plug in everything. So little a is 35, little c is 30. I put in the a and the c. Angle b is 25. So just kind of plugged everything in its place, and then I did a little bit of simplifying. And then here's a little bit more simplifying. And then, of course, to get b, I'm going to have to take a square root. Now, you guys might be thinking, hey, whoa, hold on. Why did you not put b in absolute value bars? Well, I'm finding the length of a triangle. Is there any possible way that b could equal a negative number? Nope. So then we know we're getting one answer. That's it. Done. So I did my calculation, and I got that little b is about 14.9. What if I wanted a missing angle? I'm going to tell you, law of sines will always be preferred if you're trying to find a missing angle. The problem is, law of sines requires an angle in the triangle in order to find a missing angle. Law of cosines is for this kind of situation, when I've given you the three side lengths, but none of the angles, because law of cosines uses three sides and one angle. So that's what makes this one more useful. So I'm going to grab the little b version. Again, it makes no difference. It's three sides, this multiplication, and the angle. So all I need to make sure I do is, because I'm looking for angle B, it just means that the B length needs to be the one over on the left. So we solve it down. Put in 20, 28, 30, did some simplifying, did some more simplifying, subtracted 1684 to the other side, divided by the negative 1680, did an inverse cosine because I'm trying to get the angle, and I get that angle B is about 40 degrees. So now that you know that angle B is 40, do you think you could solve the triangle? Solving a triangle means take the picture and make sure you know the length of all three sides and all three angles, no matter what, using your laws to find it. Well, I've got my three sides. What I need is another angle. I could use the law of cosines again if I really wanted to, but law of sines is just so much simpler. So I'm going to use the law of sines. I am going to go after what I'm calling angle C. It's the angle across from the 30 side. So sine of 40 to 20 is the sine of that angle to 30. So multiply by 30, do an inverse sine of that disastrous mess, and I get that angle C is about 75 degrees. Now we know by definition, if I add the three angles of a triangle, it's 180. So if I add the unknown angle A, angle B, which was 40, and angle C, which was 75, I end up with angle A is 65. So I now know all three angles, and I know all three sides. So I hope you enjoyed your enrichment. Certainly, if you want any feedback, send me pictures, send me emails. I'll be happy to help. These two laws have some really neat applications as you get into things like architecture and surveying and engineering. So if you find this interesting, you should explore a little further. Good luck and have fun.